Hello, welcome to another session on math for data sciences. So till now we have been looking into some of the discrete distributions. We looked at 5 particular discrete distributions. As you can see, we looked at uniform distribution, binomial distribution, Bernoulli, geometric, and Poisson. So one thing to note here is in each of these distributions, the values of the random variable x, which is described to have one of these distribution, let's say a binomial distribution with the parameter n equal to 5 and p equal to 0.5. So this is very similar to a case where we are throwing 5 coins, and we are trying to model the number of heads, and we are assuming that each coin toss is a fair coin toss. For fair coin toss, the probability of getting a head is equal to 0.5 for each of the 5 trials. Now, if we are throwing the coin 5 times, the total number of heads that could come would be either 0, 1, 2, 3, 4 or 5. So there are no other possible values for this random variable x, and this random variable x represents the total number of heads in 5 coin tosses. Now, if we generalize this, if we look at the distribution, the definition of binomial here, we see that for parameters n and p, for the binomial distribution, the possible values of x could be 0, 1, 2 till n. That is 5 in this particular example. Similarly, if you look at Bernoulli distribution, where there is only one trial, you can either have a 0 or a 1 as the possible values of the random variable. Similarly, now if we go towards geometric distribution, if you remember, the random variable is defined as total number of trials required to get the first success or first successful trial. Now you would obviously need at least one trial. So let us say we are modeling the total number of trials required to get the first head. Once again, we are assuming that the probability of getting a head is still 0.5 for each of the trials, and we are modeling x as the total number of trials required to get the first head. Now we can either get the head on the first trial, or we can have th, tth and so on. Therefore, the possible values of this random variable could be 1, 2 and so on till infinity. So we can always keep getting tails, which would be highly unlikely and very low probability, but still we can have a case where we are keep getting, and therefore the value of x can be as large as possible. Now one thing to note here is, even though x could be as large as possible, almost tending to infinity, the values of x are still countable here, and they can be put in a discrete way. So for example, let us say you pick any two values of x, any two possible values of x. Let us say we pick a value m, and we pick a value n which is higher than m, and now there would be obviously some other possible values between them. Now the thing here is, in any of these two values of m and n, we know how many values exist between them. So this is one of the important property of a discrete distribution, which is very different from the continuous distribution, which we will be introducing in this particular session. So once again, let us say we pick a value 3 for this geometric distribution, and we pick a value 6. We know that there will be 6 minus 3 plus 1, which is 2 values between these, and these are 4 and 5. So we always know there are countable number of values between any two values of x in a discrete distribution. Now just for completeness, for Poisson distribution finally, since Poisson distribution represents the total number of arrivals happening in a particular time interval, there could be 0 arrivals as well. Therefore, the value of Poisson distribution with any parameter lambda, the value of the random variable could be 0, 1 and so on till infinity, since the number of arrivals could be as large as possible. So now we'll try to differentiate on the basis of this property for continuous distribution. So for that, we obviously need to know what are the different kinds of continuous distribution, but let us say right now you can just assume there's something called an exponential distribution. So once again, we'll be looking at these in way more detail, but right now just to explain what the major difference between discrete and continuous distribution and taking this particular example. Now a continuous distribution is represented by a PDF, which is called a probability density function. So once again, I'll explain how probability density function is different from probability mass function, which we looked in discrete distribution. But right now, let us say we assume that there's something called a probability density function defined for continuous distribution, and for exponential distribution, it is defined as lambda times e to the power minus lambda x. So what this gives is, it gives you a value for each x value. Lambda is a constant here. Lambda is a parameter for exponential distribution, just like we had different parameters in discrete distribution as well, like n and p for binomial. We have lambda as the parameter for exponential distributions. Now, if we make a graph for this particular distribution or function, we'll see we'll get something like this. And this is something called an exponential distribution probability density curve. So we call it probability density curve. So yeah, I mean, I'm throwing a lot of jargon here, but I'll be explaining each of these in way more detail. I just wanted to first show what is the major difference between discrete and continuous distributions. Now for this continuous distribution, if you pick any two values of x, let us say we pick 2 and 4, the values possible for x between these two values is actually infinite. Why is that? We can have the value of x as 2.1. We can also have the value as 2.111. Let us say we can also have 1112 and so on. Therefore, there are infinite many possible values between 2 and 4, and therefore we only can represent these set of values on a continuous scale. And this is the reason or the major difference between a discrete and a continuous distribution. So for continuous distribution, once again, we can have infinite many values between any two x values, as you can see in this particular example. So continuous distribution, there could be infinite values between any two values of x. So now we'll explain this concept also by differentiating between a PMF and a PDF. So this is probability mass function and this is probability density function. Now again, for explaining this, we'll have to take some examples. So for PDF, for the case of continuous, we again look at exponential distribution. So let us say we take an exponential parameter lambda equal to 2. So the PDF is given as 2 e raised to power minus 2x. While for probability mass function, let us say we take a geometric distribution here with probability again 0.2. And if you remember, geometric distribution is the number of trials to get the first successful trial. Now the probability of success is 0.2. Therefore, the probability of getting a non-successful event is 1 minus 0.2, and there will be x minus 1 unsuccessful ones, after which we'll get a successful one for which the probability is 0.2. Now this is a PMF or a probability mass function, while this is a PDF or a probability density function. Now what is the difference between PMF and PDF? I think the best way to explain this is using something called a visualization of these functions. So So now that we know what a probability mass function is, and probability mass function is defined for discrete variables, and then probability density function is defined for a continuous random variable. So we'll just try to plot them on each one of them on a graph. So for continuous one, I have already done it in just now for exponential one, and we saw it looked something like this. Now for probability mass function, this was actually called a probability density curve. Now for probability mass function, we cannot really have a probability density curve because the value of the function, this particular function, is only defined for whole numbers. So if you remember, geometric distribution can only take values which are positive integers, but it can be till infinity. So let us say we have 1, 2, 3 and so on. Now for p x equal to 1, the value is 0.2, px equal to 2, the value is 0.8 into 0.2, which is 0.16. Now for 3 it will be 0.8 square into 0.2, which will be 0.64 into 0.2, which is 0.128, and so on. So you can see the probability is actually decreasing here. So if we take this value as 0.2, what we do is we use something called a bar chart to represent these discrete probabilities on a graph. Sorry. So if we make a bar chart is nothing but we just make vertical rectangles at each value of possible x. So we have 0.2 for x equal to 1, then we have 0.16. So let us say it lies somewhere here. Then we have 0.128. So it keeps decreasing for each further value of x, and so on, for it goes till infinity. Now the thing to note here is for bar chart, there has to be a gap between each rectangular bar. So as you can see, so the main property of bar chart is that there should be gap between these two rectangles here. So whenever I'm drawing them, I'm making sure there is some gap between these vertical rectangles. Why I'm saying that? Because there, you guys must have also seen a particular kind of chart where we have something so in this case, as you can see, the bars are actually joined. And why? So how this is different from a bar chart? This is actually called a histogram. And what we do here is we, instead of looking at discrete values like 1, 2, 3 and 4, we look at ranges here. So we look at range of values. So let us say we are looking from 0 to 1, 1 to 2, 2 to 3, 3 to 4 and so on. Now how we do that is, let's say we have a distribution which has a value from 0 to 0.1, and the probability of this distribution to lie in the range 0 to 0.1 is 0.1 or say 0.2, and then we have 0.16, 0.128, 1 to 2, 2 to 3 and so on. So instead of using discrete values as the values of x, we are actually using ranges of x to plot this kind of a graph, and that is how it can be differentiated from a bar chart. So it is possible that you have a distribution where the possible values of x are, let's say 0.1, 0.2, 0.5, 1.1, 1.6 and so on. Now instead of plotting each one of them in a bar chart in a discrete manner, you will have too many values of x, and you might not want to have that in a bar chart, because then it will become something like this, where there will be too many vertical bars on the single chart, and it would be difficult to know the shape of the distribution for this kind of a data set. So for that, what we do is we combine. So let us say we have the probability here, and let us say this is 0.05, then 0.1, 0.05, 0.1, 0.1, and 0.1. Now what we do is we'll count the values from 0 to 1, and we see there are first three values of x lies in the range 0 to 1, and the sum of these probabilities is 0.2. So that is how we can get the probability for a range of x of values. We sum up the values of probabilities in that range of x values, and we get the new data set in this particular manner, and we then plot this particular ranged data set in a histogram to get a shape of the distribution for different ranges of x. So this is how we get the histogram. Now one thing to note here, how do we get the probability of a particular PMF or PDF from these different three kinds of charts which we have looked at? So for bar chart, it is very easy. You simply look at the height of the bar for a given value of x. So let's say if someone is asking you what is px equal to 3, you simply look at the height of this x equal to 3 graph here. You go to the y-axis, the corresponding value, let's say, is 0.128. You get the required probability 0.128. For histogram, again, for histogram you can only calculate the probability for a particular range. Obviously, if you have, let's say, if you are given that p0 x1 from this particular height comes out to 0.2, you cannot really calculate the value of x equal to 0.2, which was 0.1 if you remember in our example here, but you cannot get that using histogram because it's a summarized way of plotting the data, and therefore you cannot backtrack and get the required exact probability for x equal to 2.2 just by looking at the histogram. You can only get the probability for the range of these values of x. So this is how you can get the probability from a histogram. Now for the probability density curve, let's look at it in a little more detail. Let us say this is a probability density curve. Now let us say this is 1, 2, 3, 4 and 5. Now since probability density curve is defined for continuous distributions, let us say we have an exponential distribution here with parameter lambda equal to 2, and we have the PDF defined here as 2 e to the power minus 2x, which is plotted in the chart as shown here. Now if someone asks you what is the probability of this distribution having a value of x equal to, let's say, 1.5. So for continuous distribution, the probability of x taking an exact value is approximately always equal to 0. This is because there are infinite possible values of x. Since there are infinite possible values of x between any two x values, let's say we take the range x equal to 1 from here to x equal to 2, there will be so many infinite values that if you keep adding x equal to 1.1, 1.111 and so on, it has to be some value. So let us say it is 0.2. But now since these terms itself are infinite in nature, if you divide 0.2 by infinity, it comes out to be approximately 0. So for a continuous distribution, the probability of the random variable taking a discrete value or an exact value is approximately equal to 0. So one has to remember, again, for a continuous distribution, the probability of the distribution taking an exact x value is approximately always equal to 0. So then how do we calculate the probability for x. So this will be very similar to how we look at a histogram. So instead of looking at an exact value of x, we calculate the probability in a range of x. So for continuous distributions, we compute probability for range of values for x. Now how do we do that? So in histogram, we were easily able to do that by just looking at the height of the histogram for the range 0 to 1. So we can just look at the height of this particular bar and get the required probability. But in this case, if you notice, between x equal to 1 and x equal to 2, the height is actually decreasing since this is a continuous curve. So what we do is, instead of looking at the height, we simply look at the area inside the rectangle region here. So what we do is, probability of x ranging from x equal to 1 to x equal to 2 would be area of graph under the curve. So we are only looking at the region which is under the curve here. This is called probability density curve. So we'll just mention it again here. This, whatever we are looking at, is probability density curve, and this is defined for continuous distribution. So it is area of the graph under the curve in the given x range. Now, if you remember, how do we calculate the area under a continuous curve in any x range? It is actually calculated using an integral from 1 to 2, because that is the x range which is required, and we simply integrate the function with respect to x. So this definite integral will actually give you the area between the curve and the x-axis, and we are integrating it in the range 1 to 2. Therefore, we get the probability of x lying in the range of 1 to 2. So this is how we compute probabilities for continuous distributed variables using integration or using area under the graph in the required x range. So here, once again, just revising what we looked here, we looked at what is the major difference between a discrete and a continuous distribution. We did that by taking an example of exponential distribution, where we saw that there are infinite many values possible between any two x values for exponential distribution, which was very different from any of the discrete distributions which we have looked at earlier. For discrete distribution, there are only finite countable values between any two x values. That was the major difference. Then we looked at visualization to differentiate between discrete and continuous distribution. So for discrete distribution, there is something called a bar chart, where you represented for each x value, you have a rectangular bar, and the height of the bar represents the probability for the random variable to take that particular value of x. And one has to ensure that when you see a bar chart, there should be gap between the bars, because each bar represents a discrete value, not a range of values. And then we looked at probability density curve, which is a continuous curve defining the function values for the continuous random variable for different values of x. And then finally, we also looked at histogram, which was used to get the probabilities of x when x lies in a particular range of values, and the bars in this case, unlike the bar chart, are joined with each other, and the ending value of the previous range is actually the starting value of the next range in the histogram. Then finally, we looked at how can we get the probability for a continuous distribution under the PDF or under the probability density curve. What we do is we simply integrate the given function, probability density function, with respect to the random variable x in the required range 1 to 2, for which we are calculating the probability. So this is it from this particular session. In the next one, we'll be looking at the first continuous distribution, which is uniform distribution, and we'll be looking at a lot of properties, what we can compute using simple calculus. We'll be calculating a lot of metrics for a continuous uniform distribution.